is going to be focused on stateful and stateless patterns in Kubernetes. And it's really an excuse to talk about how to deal with various features, various use cases when you want to run stateful application in Kubernetes together with stateless. So my name is Nick Vermandé. I run the DevRel team at Spectral Cloud, which is currently a team of one. So I'm recruiting also developer advocates or DevRel engineers. If you think you can be a good fit, you can go and come talk to me after the talk. And if you're watching on YouTube, you can find me on any social network, LinkedIn, Twitter, whatever. I spent the last 6 years working on Kubernetes, also at Cisco, working more on the CNI aspect, then StorageOS/OnDat, working more on the CSI storage aspect. And during those time, I've been helping a lot of customers adopting Kubernetes. And this talk is really like a lot of things I've noticed with customers and the challenges they were trying to solve. So other than that, yeah, I enjoy coding DevOps tool and automation tools. I love metal and I love running. Not both at the same time. Probably listening to music, yeah. Not doing music at the same time. So first off, does a system or does a stateless system just exist? I think the answer is no, right? Any Turing machine or Turing complete machine does store some state. Like a computer, even in memory, does store some state. So there's no such thing as a stateless system. It's just an architecture pattern. And when it comes to Kubernetes, I would say the rivalry between stateless and stateful comes down to different things. We're going to see now what are the differences. But I remember, I don't know, maybe you remember too, a couple of years ago, when really containers started to catch up and become the hype. We were told that containers should be short-lived, which is probably true. But over time, Kubernetes has developed many features that will help you run stateful application directly in the cluster. So I would say that now it's not an anti-pattern anymore, and there are ways to do it, and we're going to see this in a minute. But first off, where does it come from? Why stateless? I mean, of course, because we are using containers, and containers by default, they are immutable. So immutability and the fact of being stateless or stateful are different things, but because containers are immutable, it means that if you need to write something to disk or change configuration and apply it to disk, you cannot really do that. I mean, yeah, you can, but should you? The answer is probably not. It should stay immutable. Don't commit your changes directly into your image. You should build a new image and replace all the container with that image. That's pretty obvious. And then comes the 12-factor app. So who is familiar with this 12-factor app? You probably have the room. So if you're not, I encourage you to go on that website that will basically describe all the features that a cloud-native application should have and how you should implement them. So it talks about the data state engine. And if you follow the principle of those 12 principles, one of them is that the code should be stateless, or should not be mixed, rather, with your stateful component. Anything that is stateful, such as a database, message queuing, even a cache, should be treated as an external resource, or as an attached resource. And if you still follow those principles, attached resource means something or a component that can easily be reattached or detached, something that is loosely coupled with the rest of your application components. So essentially, it means that whatever application you're building, you need first to sort of explode it if it has any stateful component so that you can run your, let's say, front-end code or stateless code in a separate set of container or pods in Kubernetes. And then you run your database, message queuing system, or anything somewhere else. But the question becomes where, right? So, of course, you can run on S3 buckets you can run on PaaS services, SaaS services, whatever you want. But you can also run those stateful service in container. But the challenge then becomes, how do you mount volume into container? How can you do this in a way that will guarantee the storage is not lost in the end? And again, it started with bare naked container. If we look at Docker, since the beginning, you could do bind mounts. So bind mount in Docker simply means that you have a directory existing on your host, and you can run this type of command when you specify the source, the target, and the name of the container. As easy as that. But it was not ideal. Then you had name volume in Docker, which probably is the way to go, because the volumes are entirely managed by Docker. They don't pre-exist as part of the host basic system. And another evolution of that is volume plugin in Docker, where you had the ability to also incorporate other solutions into Docker, like that particular example is for block storage. You can run in DigitalOcean. So suddenly, in a container, if you're running your container maybe in DigitalOcean, you can mount volumes that are part of another service that the cloud provider is offering to you, in that case, block storage. But now, how about Kubernetes? So here is a quick timeline about the lifetime of Kubernetes with the birth of the CNCF in 2015. You can see that 2016, which is quite early, Kubernetes started with StatefulSets. Originally, it was not called StatefulSets, it was called PetSets, right? But the name was not so good, so hopefully now StatefulSets is more meaningful in terms of what that is. But it was always a thought, like, thinking about the future. At some point, it's not only about having stateless and pods and stateful pods being an anti-pattern. Is always, can we bring those workloads closer to Kubernetes? So now I'm going to go through various patterns you can apply and different features, and then depending on the pattern, can be stateful or stateless. First off, application configuration and data. So whether you run a stateful or stateless application doesn't really matter. At some point, you should not code, like in directly into your application, right? If you have any configuration, you should not hardcode them in your code. Right? It should be part of the platform. And how you inject this information in Kubernetes, different way to do that. And this is what this pattern is about. So we have, if you do this command, so I don't know if you're familiar with that command, which is great in Kubernetes. It took me like 6 months before discovering that command, which really helps. kubectl explain, and then you can specify, any objects or any features, anything like if you follow the API kind of naming convention. Here it's pod, which is related to the pod object, spec, volumes. -- recursive will give you from there to the end of time everything that is possible. Very, very useful. So it gives you like a couple of volumes. You can use PVC, which we're going to talk about a bit later, persistent volume claim, which is preferred for storing data for stateful workloads. MTDR, which is essentially a scratch type of temporary space that can be defined as disk or memory, if you wish so. If you use memory, it will count towards the memory limit of the container as well, so you have to be careful. Host path, which is local to the host, like a local directory that is located on the host. Config map that you can mount as volume, right? So that's a good way to insert any configuration for your application into Kubernetes. Secrets that you can mount as volume. And finally, the downward API. So the downward API, same thing. When I started, I was like, what is this? So downward API gives you the ability to add context into your pods. So you mount this as a volume, and you can reference things, so the field ref and the resource field ref that are contextual to the pod. So you can get information on your disk here, like read information from file, things like namespace, label of the pods, known name, pod IP, things like host IP, current resources limit configuration. All of that can be injected into your application by simply using the downward API, right? So those are all the volumes. Some of them can be applied to stateless application, and some, like PVC, is more used for stateful. Another pattern for an application is what we call a singleton. So a singleton is simply an application with the number of instances equal to 1 for the pods. So typically, you could run a naked pod, but it's not very efficient because why people are using Kubernetes is because Kubernetes guarantees high availability. If you just deploy a naked pod, if the pod dies or the node dies or you delete the pod, it won't be recreated. So you need a higher level controller for that. So example of singleton, like anything that needs to treat something once, a transaction once, like write to a database, depending on the previous action, previous task, consuming messages, all of that is a task for a singleton. So the best way to do it, of course, you can do it in the application by implementing some sort of semaphore in your application. But if you want to do it in Kubernetes using a pattern, you can simply use replica set or StatefulSets, set the number of replicas to 1, and of course use the health probe, so liveness, readiness, startup probes to guarantee that the pod will be restarted in case of application issue. Another thing which is kind of the opposite of what we've just seen is the pod disruption budget. So a pod disruption budget, this feature, the goal is to limit the disruption of the application by either specifying the maximum of unavailable pods you can tolerate, or the minimum number of available pods at all time, but it's only guaranteed during voluntary disruption. So what that means is if you drain a node, if you delete a pod manually, this will be, or update an image, for example, this will be guaranteed. But in case of node failure, for example, this won't be guaranteed. This is not how you can manage, like the disruption, limiting the disruption of your application this way. So here's just an example. You can use either numbers, like minimum available or percentage. And also you cannot use both min available and max unavailable at the same time. Another pattern. I'm trying to go rather fast because I've got a lot to cover. What time is it? It's been like 15 minutes. That's already half. So I'll need to, multiply by 2 like you watch videos on YouTube. You never do that? But you listen to courses 2 times faster. Yeah, that works. So persistent data, this is something that sometimes is difficult to grasp for people who are used to use deployment in Kubernetes and just containers, not stateful sets. So the moment you want to store individual, let's say, information in every pod, there's 2 ways to do it. Either you use a normal deployment. In that case, you will need shared storage. You cannot define local, individual, persistent disk space with a deployment. If you think about it, when you create your deployment and the template, you specify your volume definition. If you specify, let's say, a local volume, if the first pod that gets deployed will lock that volume, like on the node, and start writing to it, right? Another pod, well, this local volume, if it's on another node, won't be accessible first. And if it's on the same node, well, it will stay in pending state because the local path has already been acquired by the first one. So this is if you use read-write once sort of storage for your pods. So the only solution is to use shared storage, typically NFS, and then per pod you can create your own directory, and that's fine. Or that's fine, depending on what's the intent. If it's a database, you're going to have performance issues, right? Running a database on NFS is not a good idea. And this is where StatefulSets may come at the rescue. So if you see here on the right, StatefulSets looks like deployment. The only thing here is at the bottom. You can see that you can allocate persistent volume clade individually on a per pod basis. So they will all write to their own dedicated space on the node they are residing, right? So it can be, again, it can be shared storage or local storage, but the point is it can be read-write once, right? This is where you can have SSDs and NVMe for real performance. So yeah, and we're going to see in a moment how to define how it works and how to define this individual persistent volume claim. This is like a, let's say, simplified view, right? Just to show you that here on the left, stateless, on the right, stateful, right? If you want to have every pod writing to the same storage on the left, it has to be a shared file system. So if we look a bit more into StatefulSets now that you understand, the basic principle, which is to run individual application and individual pod, and each of those pods or container will have their own individual characteristics. So it starts with a stable and persistent identity, meaning that a stateful pod, so when I say a stateful pod, it means a pod that has been deployed by a StatefulSet controller, right? So a stateful pod will always have the same identity. So starting with ordinal number 0, so you will have mypod-1, 0, mypod-1, etc. It's going to increase over time. If the -0 dies, or the node hosting the pod, no, not the node, if the pod dies, or if you delete it, it will recreate exactly the same one. That's a major difference as compared to a deployment. If you delete a pod, the pod will be restarted with a different name, different IP address, different DNS name. If you had like local path or any storage attached that is not PVC, will be scratched, right? That's one of the main characteristics. The pod will have the same name for a stateful pod. Won't have necessarily the same IP, but will have the same DNS name as well, right? Which is really important. So they can have, they are meant to have long-lived persistent storage through the persistent volume claim, and more specifically, you define it with the volume claim template. So now you have an extra layer of templatization, right? Deployment, stateless, you have a layer, you have the pod template, and that's it. StatefulSets, you have the pod template, and now on top of that, you have the volume claim template. And you define this volume claim template in such a way that now every pod that's going to be deployed can consume its own persistent volume claim, all right? So one volume per pod, you need to use a template for that. And this is why volume claim templates are used with StatefulSet. Another thing that the StatefulSet controller guarantees is that you will have at most one pod with a given identity. So it's what we call the at most one semantics versus at least one semantics for deployments. So what I mean by that is if you update a deployment, chances are that at some point you will have a surge. You will have more pods than expected. Right? With StatefulSet, that doesn't happen. Right? If you need to update a StatefulSet, we're going to see how it works. But basically, it's going to delete a pod, update the pod, finish. Delete a pod, update the pod. There's no such thing as at some point you may run with more than expected. Because if you think about it, if StatefulSet would do the same thing, imagine a database cluster. Suddenly you add a container, like a new database member, and you remove it after, that cannot work, right? The application needs to be aware of what's happening in the infrastructure. So StatefulSet, we have the guarantee of one pod at most for a given identity. We're going to see also partition updates in a moment, but the idea is to provide canary deployment for StatefulSets and also parallel deployments. So first, I want to talk about the volume claim templates here. So as I was saying, inside the volume claim template that you specify for the StatefulSets, what you can do is typically what you do is just use a storage class, because then everything is automatic. So in our case, I have a StatefulSet single volume claim template, I'm just using a particular storage class. And if I define 3 replica, automatically without doing anything, I will have 3 PVCs and 3 PV. So this is the simplest possible configuration for a stateful set. Start volume claim template, use a storage class, and obviously you need to have your CSI driver, your storage, your storage software, your driver for your storage. And because most of the time it's going to be dynamic, meaning that you don't have to create the PV, the PVC, and link them together. Just use a storage class. When you create the stateful set and apply the configuration, everything will be created automatically, right? So that's very easy to do, provided you create the volume claim template and you have a storage class available. So I was talking about the name resolution. So here, this is an example comparing stateful set and deployment. So stateful sets doesn't have any cluster IP associated. So you cannot access the service like that, right? You have, when you query the service, it will return the list of all the IP, right? As opposed to a deployment, if you query a service that has a deployment, it's just a DNS round robin. You will have one IP return. With the stateful set, you do a DNS query on the service, no cluster IP, and it will return a list. So it's up to the application to select one IP from the list. But I believe that every time you do a query, the first one is never the same, right? It's kind of round robin as well, but it returns the full list. Other than that, you can access the pod name and IP in the same way. So the main difference is this headless service, what we call headless service. No cluster IP, and the DNS server returns the full list of IP address. So partition rolling updates. So it's a complicated word, just to say that so by default, as I said earlier, when you if you want to change the image, right, you want to do a rolling update on a stateful set, is going to start with the first pod and then updated, waited to be ready again, et cetera, until you reach the end. You may want to do a canary deployment, like in 2 different parts. This is what it enables. So if you set these settings here, so spec update strategy, essentially, partition to 2, so from 2 onwards, so equal or greater than 2, you will be able to do 2 updates, like a partitioned update. And the parallel deployment, which is, in my opinion, it should not be changed. Order ready, which is exactly what I mentioned before. So starting with the first pod. Parallel means that all pods from the stateful set will be updated at once, which can be dangerous, right? For testing, maybe that's good. Or if your application doesn't have any, if it's not like a database, or if you're brave enough, you can try. It will go faster for sure, but not sure it's gonna work. An interesting thing is node failure, right? So node failure with a stateful set is quite interesting because if it's for stateless deployment, stateless container, it's easy. A node fails, the API server waits for the pod eviction time, and then mark the pod as terminated, and suddenly, the pod can be recreated on whatever node. Stateful set is not the case. It will wait forever until something happens. So the API server monitors for the controller, the pod controller, the controller manager will send a message to the API server, hey, pod eviction timeout is over for this pod, but well, the API server won't do anything. So a couple of actions you can do. If the node is dead for good, remove the node object, kubectl node delete, or delete, yeah. Or wait for the node to come back online, another solution, or force the pod deletion with kubectl, but you have to proceed at your own risk, right? It can be dangerous. So this is this line, and if you still have issue, you can force it with deleting the finalizer, setting it to null, meaning that okay, I don't have any finalizer anymore. And also, if you want to fence fast, or fail fast with fencing, some storage provider, some CSI driver will do it for you, right? So if you use what we call container-attached storage with a storage layer inside Kubernetes, some of the solution will, feature will guarantee that in case of node failure for StatefulSets, it will recover super fast because it does have replication, right? Most of the time, your CSI will implement replication, and then another node can take the pod over, right? Because the storage is already there somewhere else. So now, in terms of storage patterns. So the storage class, as I was mentioning before, is super useful. Always create a default one at the beginning. If you use Google Cloud or any sort of managed Kubernetes cluster, it will be there by default. So storage class will allow you to create all the storage dynamically. So normally you have persistent volume, which is the real storage, persistent volume claim, which is basically the claim, and essentially it's exactly what a pod is to a node, right? It's just, so the PV is the resource, the PVC is consuming the resources, like a pod is consuming node resources. So the PVC, once it's created, you bind the PV to the PVC, and you can start using the storage. Here is the storage class. Again, everything is created automatically. Storage class has reclaim policy, so that a PV can be deleted or retained if you delete the PVC. It can also respect topology, specific topology. So what that means is if you have storage on different nodes, you may want to guarantee that the scheduler will still be able to satisfy the different affinity, right? So you have to be careful with this. It's called, so the binding policy can be immediate. In that case, you bypass all the constraints, or you can do wait first consumer. In that case, you will leave the scheduler do his topology constraints. And also, you can define the volume plugin to use, depending on the storage. Can be NetApp storage, Storage OS, or Google Persistent Disks. So you will have different options, right? And you can find many of those CSI providers. I give you an option here with Storage OS, or now on that, where you have you can basically for the whole storage class. Define the file system, the number of replicas for your volumes, these kind of things. And then it will be applied to every storage or PVC and PV that are part of the storage class. It's like a template, right? And as I was saying before, you can do some more advanced feature like replication, encryption, caching that are brought by the CSI. They are not native to Kubernetes, but if you want to run stateful workload at scale, you have to be aware of those extra features you will need in Kubernetes. And they are provided via the CSI driver. And so those CSI drivers usually use container-attached storage, which means that you're now running an extra storage engine within Kubernetes, so it's an application itself. Most of the time, it will take ownership of your local storage here on the bottom, whether it's NVMe, SSD, HDD. Some of them support different tiering. And then it will create this extra storage engine on top, still an application running on Kubernetes, and expose it to consume to your Kubernetes pods and add those volumes, like in red here. You can use those volumes as part of a storage class, right? And the PV, PVC, etc. will be created based on that storage class. And this is how you configure also those extra features, right? So once you have this setup, this storage class setup, this is where you can configure the number of replicas and things like that, adding feature to your storage environment. So a couple of things to finish. So now there's another thing that is really key to running your stateful application. It can work with Stateless, it's not related, but Kubernetes operators are a way to encapsulate knowledge about your operations. So it allows you to simplify the deployment, scale-out scaling of cloud-native applications, stateless or stateful, doesn't really matter. But when used with stateful application like a database, it can not only, as the stateful set is building and the number of replicas are increasing, it also builds the application layer on top. So you have the infrastructure layer that is all the features are guaranteed by Kubernetes that we've seen so far. But now with the operator, you can go one step inside into what is installed on those pods. So typically, here you have a MongoDB Enterprise operator that gives you this extra knowledge and how to do things like backup, how to deploy your MongoDB application by guaranteeing that you will have a cluster of 3 nodes that is formed. And if you increase that number of replica to, let's say you have 3, if you want to increase to 5, then the same operator will guarantee that you will now have a 5-node cluster that is up and running, right? And the last thing in terms of what you can apply on top of it, because operator, again, they define custom resources representing your database, for example. And because they are written in YAML, it means you can apply any Kubernetes native principle, including policy as code, right? So policy as code include things like, gatekeeper, Kyverno, Daytree, that allows you either to modify things in production or even in DevOps pipeline allows you to verify that the database has been is ready to be created with the right settings. And then this one, and this is the last one. This is more about building your cluster in the cloud in different availability zone to guarantee this high availability across different regions. So typically, in terms of compute, you can control the topology Kubernetes.io, this particular label. You can define zones. And then you can apply what we call topology spread in Kubernetes that guarantees you have your pods evenly distributed among the nodes that have different label associated with this. And if you have the right CSI, you can do exactly the same thing. So spread your replicas of your PVCs, replicas across different regions, so that when a zone or a region dies, you can recover in another region. So again, this is some of the best practices you need to make sure you align with, and one of them is choose your CSI solution with care, right? So here are, just for your information, some of the best practices I've mentioned during the talk. So yeah, you can take a look at it. So that's all. That was a lot. Sorry, I'm a bit late, but hopefully it's been, I've managed to gather a lot of information from the past year, so hopefully it was useful. Thank you.
Thank you. Come with me. Take your water.
I don't know if we have time for a couple of questions.
We have a few questions, and we have a bit of time, but I promise you will be out at 6 p.m.
Yeah, anyway, I'm the last one, so we can stay the whole night anyway.
Yeah, let's do that. It's a good idea.
Put some music
let's just have a little tech sleep over. With the rise of operators, do you think StatefulSets will be replaced by deployments with better just-in-time controllers for each stateful workload?
OK, so this one, I'm not 100% sure. I love the idea of building stateful application with operators, but there are, I saw some use cases where an operator was essentially building a different deployment for every pod. I think that was the etcd operator from Improbable who is doing this. So the point here is it will depend on your use case. If it's a super complex use case and you have the power to do it with the right resources, you could eventually create an operator and not using StatefulSets at all. But you will need a lot of developers and people to maintain that. I would say first I would go towards more like the StatefulSets operator first. Yeah.
How does a stateful set respond to a node with a replica on it being drained? Is it the same as a regular deployment?
Does a node being drained with a replica? Yeah, it will be, because it's a manual action, it will be the same as a regular deployment, right? But it will be the same as a regular deployment.
What about video streaming services? They look like fully stateless systems.
I mean, probably there will be different components in such an application. So I'm assuming like the main part is stateless, but you may have to store things on disk. In that case, you would use potentially a stateful set for some aspect of the application, or at least some PVCs, right? So I would say you won't have, and this is part of the the 12-factor application definition. And your application should not be just a single pod. It will be composed of several of them. And I'm assuming, like for video streaming, some of them will be stateless, but at some point you may need some stateful component. In that case, I would go for a stateful set for sure.
How's consensus in the system reached, for example, for outlier detection or when two clusters publish?
Sorry, I can't.
You want to read it with me?
So how is consensus in the system reached for outlier detection or when two clusters publish conflicting information? So I need to read this again. So how is consensus in the system reached? Okay, for outlier detection. Two clusters. So I don't get where is the word two clusters coming from. In different Kubernetes cluster, you cannot run stateful sets as the same stateful set as part of two clusters. So here, if I'm assuming like a single cluster in an application, so yeah, if you have a node failure, and let's say you have a stateful set with a 3-node database, you have a node failure that has one database. That pod that runs the database won't be restarted anywhere because it's part of a stateful set. So you rely on the application layer to take action, but you want that to be a transient state. You don't want that to last for too long, right? Because you are at the risk to lose another node, and you're in a degraded mode. So what that means is, as I stated earlier, you should take action as early as possible using alerts, Prometheus, whatever, to know that a node has failed and it needs manual action. You can probably automate that if you're, again, with an operator. You can write any sort of automation. So you can write some scripting or an operator or something to take action. But yeah, currently, there are some proposals, like if you watch GitHub a little bit, some proposal around how to change and make it better. But at the moment, this is the only solution, unfortunately.
Okay.